Chapter 12 introduces the idea of rotational motion. Up until now, we've only been talking about translational motion, or linear motion, and now we're thinking about rotation. Not only is this important for objects that rotate around a fixed axis, or their center of mass, but you also have combination motion, where you have rotation and you have translation. So all of the topics that we introduce in this chapter are necessary for talking about pure rotational motion, but also combination motion. So the first idea is the center of mass, which is calculated for a continuous object based on these integrals, but there's a simpler form if you just have individual pieces, like particles or balls connected by rods. The center of mass is important because that's going to tell you about how it balances, that tells you where the force of gravity acts, and that's going to be where the object will rotate around if it isn't constrained to rotate around a different place. Moment of inertia is the rotational equivalent of mass. It's not just the mass, though, it's also how the mass is distributed. It depends on r squared and each little differential piece of mass. So in general, we can calculate this either, again, if it's a discrete object or if it's a continuous through doing this integral. In general, you can use a table in the book which provides the moment of inertia for a number of different objects. That table is reproduced on your equation sheets. So you have to do the modeling to identify which of those objects is applicable for your situation. If you know the moment of inertia around the center of mass, you can use the parallel axis theorem to shift it if you're rotating around a different point that has an axis parallel to the one that was originally calculated. Note that whenever we're talking about rotation, you need to identify the axis of rotation, which means the point that it goes through your object and which way it's oriented. Torque is the rotational equivalent of force. Now, the best definition of torque actually uses a cross product, but if that's new to you, you can just use this form instead. It depends on the distance from the point of rotation, again, that's always important, and there's this radial distance where your force is applied, the magnitude of the force, and then the angle between the force and that radial vector. So it depends on r, f, and then sine of this angle. Again, it's not the angle that the object itself is at, it's the angle between your force and that radial distance. If it's a different situation, then we use the right-hand rule to get the description if you want to use the cross product. So in general, this is good for getting the magnitude, but it doesn't actually tell you the direction. So this part we didn't quite worry about. Well, there were two definitions, two interpretations, where either you can talk about the entire distance and the tangential force that's perpendicular to the radial distance, or the lever arm and the entire force. But this equation you can always use. These are two different interpretations of where that equation comes from. Then we can use, in general, axial vectors to describe the orientation of our rotation. And again, this is using the right-hand rule to say if it's rotating counterclockwise, it's up, clockwise is then down. And so these are axial vectors. Now, a new quantity that's really important is the angular momentum, which can be defined for a rigid body object as I, which is the moment of inertia, times the angular velocity. And note that angular momentum is a conserved quantity as long as you have an isolated system. So typically we use angular momentum whenever we're dealing with a system that is changing, but not due to any external torques. When you do have an external torque, that changes your angular momentum, and this equation is very analogous to how a force changed our linear momentum. We have three new models in this chapter. First, and the most important, is the rigid body model. Up till now, we've been using the particle model, where we don't care about the size or shape of our object. We make it be a particle. Now, we actually care about the size and shape, but we're assuming that the size and shape of our object is staying fixed throughout our motion. So decide whether you want to use the particle model or the rigid body model for each object, and in some cases you might use the rigid body object model for one object and the particle model for another. An example of that is when you have a pulley, which is a rigid body that you approximate as a cylinder, and maybe there's a bucket hanging from it, and in that case you can maybe model the bucket as a particle. A second model is the constant torque model. This is analogous to the constant force model. So in this case, we're assuming that the torque itself is constant and that it causes a constant angular acceleration. Note that we have some kinematics equations back from a few chapters ago relating angular acceleration, angular velocity omega, and theta. So you can use those equations if you have a constant angular acceleration. So just like we might ignore small variations in force to treat it as constant so that we can do the math, similarly, we're going to ignore small variations in torque due to typically small variations in force. So similarly to Newton's second law, where we had force equals mass times acceleration, we now have torque, specifically net torque, total torque, equals moment of inertia times angular acceleration. The third model is also a rotational extension to something we saw in translational motion, and this is the idea of static equilibrium. So like our previous equilibrium model, we have zero net force, but now we also have zero net torque. When you set up these situations, you actually want to draw extended free body diagrams, which I'll talk about next, but you need to track all of the torques and all of the forces, keeping track of directions, and you know then that they're all total. So typically you have a lot more variables to deal with in these problems since you actually have more constraints. So I want to show an example of a new type of representation that I refer to as an extended free body diagram. And what I'm showing is an example from the book where we have a real-world situation that we are then modeling from a physics point of view. And here the focus is simply on how we draw this. So this is a fine picture. You see what's going on, but it doesn't help you set up the physics. Now this is a situation where we need to worry about torque, so we can't use a free body diagram. We can't model everything as a particle. Instead, we need to choose simple shapes, and we're then basically using just bars to represent the upper arm, the lower arm, and then we don't explicitly need to worry about the shape of the barbell because we're actually looking at the forces on this lower arm. What we then do is look at the location of each force. The other thing we need to do is identify the pivot point. So your pivot is here. This is at your elbow. So make sure that you've always identified where your pivot is, and in general, what you should do, in addition to defining your coordinate system, it's really helpful if you actually have the origin of your coordinate system be at your pivot. So we can call this x equals 0 and call this y equals 0. We then can label the location of each force. There's a force on the elbow, which is in this case going to be directly at the pivot point. The tendon is pulling up a few centimeters back, and then the barbell, in this case we're modeling right at the end of the arm, and that's down. Note that in this case, we haven't explicitly shown the force from gravity acting on the arm itself. If you wanted to do that, you would actually need to denote the center of mass of the arm. And we can denote that this way, COM for center of mass, and then we would have the force of gravity down. So whenever you're working with torque questions, especially something where you're dealing with static equilibrium, make sure that you have your coordinate system, including an origin. You've shown where your pivot point is, and each force is labeled with the location that it acts. You might also write things off to the side, like if you know that your net torque is equal to 0, if you know that your net force is equal to 0. And depending on the situation, like if you actively do have a rotation, then you might want to start to say that, for instance, this is a rod, and then you could start talking about what its moment of inertia is. So when I refer to an extended free body diagram, you're actually showing your object and showing the location of your forces.